Yes, that's fine. Thank you.
Okay, so I am going to talk a bit about my PhD project, which is part of a joint industry project called HiRise. The aim is to develop a system to reduce or suppress hydrogen explosions, and it's mainly for bigger hydrogen installations. Yeah. So I didn't know what kind of audience I would be getting, so I will quickly go through the kind of basics. If I can. There. So what do we mean with vapor cloud explosions? It's basically fuel and air that get mixed, and if this gets ignited, we'll have a chemical reaction between the fuel and the oxygen in the air, which will produce products and energy. And this energy will basically cause other reactions to happen, and you get a self-sustaining reaction that will then burn at a certain speed. So if this flame goes at or is not disturbed, it will typically go with what is called the laminar burning velocity. This depends on the type of fuel we have and the ratio between the air and the fuel. So the maximum laminar burning velocity for most hydrocarbons is about 30 to 40 centimeters per second. Well, for hydrogen, this is about 300 centimeters per second. For hydrogen, you can see here the burning velocity as a function of how much hydrogen there is in the air. So the maximum laminar burning velocity you will have at around 40% hydrogen in air. The stoichiometric concentration is around 30 for hydrogen. This is when all hydrogen consumes all the oxygen in the mixture. We typically say that mixtures above 30%, we call them rich mixtures, and below we call them lean mixtures. If you have an explosion in closed volume, you will typically get around 6 to 8 bars, depending on the fuel. And this is independent of how fast the reaction goes. It is just the energy that is generated by the chemical reactions, which will cause the products to heat up and expand. So if you open up this box, the air can or the gas inside the volume can flow outside. And you will typically get reduced pressure in the vessel. And this is basically one of the most common safety measures that we commonly have for hydrocarbon fuels. Basically, you have vent panels on, for example, a building or equipment that you want to protect, and these panels will open at low pressure, and the pressure inside your building will not get as high, so the building remains intact. Of course, a high or a larger opening will result in lower pressure inside your building, and it is also dependent on the reaction of or the reaction rate of your explosion. So this works very well for most hydrocarbon fuels, but the problem is that for hydrogen it goes so fast that you need to open up the whole building, and it's very impractical, and in most cases it's not possible. So what can we do to reduce this reactivity of the hydrogen air mixture? I often say that there are 3 different things you can do. The first one is you can inert your system by adding something that does not react, for example, nitrogen or CO2. This is often used, and it has some applications, but first of all, you need a lot of this to reduce your reactivity to, for example, what you would have for hydrocarbon fuels. You also will need to keep the atmosphere inerted, basically, throughout normal operation. You cannot basically, if you have a leakage, you cannot try to pump in enough nitrogen or CO2 to prevent big explosion to happen. So it has limited applications. You can also do it by cooling. Often water is used. You have something with a high heat capacity that will basically absorb a lot of the heat of the explosion and will not go as fast. For hydrogen, this does not really work that well. The hydrogen often goes a little bit too fast to get the real heat exchange, And in case of, for example, water, you have droplets that will induce turbulence, and you actually get a much more severe explosion as if you don't have any water in. So the third option is chemical inhibition, which is basically what I am looking at in my PhD project. So to kind of explain how this works, you need to know a bit about the combustion of hydrogen. So you all know that hydrogen and oxygen will turn into water. This reaction is in fact a very slow reaction, and in reality this does not happen. You will in fact have a lot of what we call elementary reactions, and some of them, they will basically break up your oxygen and hydrogen molecules, and you'll get radicals that are basically atoms like H, OH, HO2, and those are mainly the most common in hydrogen combustion. And when these radicals get are generated, they will basically again break up more molecules, and you will get more radicals, and it will basically accelerate, and you'll get a very, very fast reaction, at least in the case of hydrogen combustion. So what we want to do with a reaction like this, we want to add something that basically steals these radicals and combine them into a more stable molecules. This has been done a lot for hydrocarbons. Mostly the research has been done for firefighting, and in the 50s and 60s, the most common thing to use was this CF3 BR, which was a kind of a good flame extinguisher that they had at the time. Later on, they figured out that these gases were not that good for the ozone layer, so they had to find something else. So they did a lot of other tests, and you can probably see that they also found a lot of metallic salts that were actually a lot better than these halons that they used before. The most effective ones, that is iron pentacarbonyl. It is unfortunately a very toxic substance, and so are these lead and chromium compounds. However, the ones that are with potassium and natrium, they are not toxic, and they are easily available, and they are, as to date, they are the most common fire suppressants that are used. Probably know these biosuppressants you have at home, and they're filled with powder that is most likely sodium bicarbonate, or maybe potassium carbonate. In the last few decades, they've also investigated how this will work to extinguish explosions. And they've actually developed systems that work very well, where they can activate the system when they have a leakage, and they can then keep a cloud in the facility, and if the gas gets ignited, you will get a very, very reduced explosion. So what we want to do is we want to develop a similar system for hydrogen. So we have done a bit of tests with this is potassium carbonate, and you can see it works well for almost every hydrocarbon, even very fast hydrocarbons as acetylene. However, it does not work for hydrogen. So yeah, other things that are have been investigated, mostly the main study has been done by Miller in 1963. He tested a lot of different gases and fluids, and the conclusion was that actually hydrocarbons are very effective inhibitors for hydrogen. So why not use them? As you can see, for 45% hydrogen, they do work very well, and this is the concentration, which is basically worst case. So this is the concentration that this study used. However, stoichiometric, it still works. However, not as good as it worked for the 45%. And when you get to lean concentrations, for example, 15%, you're actually making things a lot worse from having laminar burning velocity that is comparable to what you have for hydrocarbons. You increase it to something that is basically a big problem. So what I've been looking into is combining these two. So I tried to add propane, and then in addition add potassium carbonate, and you can see this is for near stoichiometric mixtures. The yellow ones is without propane. You can see that the potassium carbonate almost has no effect. But when adding propane, you can actually get very reduced laminar burning velocities. And for lean mixtures, you can also reduce these or the laminar burning velocity by adding potassium carbonate to the mixture. There are still, of course, few. You need a lot of propane to get this to work, and there are some areas where you actually increase your laminar burning velocity by adding a mixture still. Yeah, so what I'm looking into now is having hydrocarbons inside these plastic containers that are kind of small, and maybe then we're again having a powder, and these plastic containers will then melt due to the explosion and release the hydrocarbons inside, and that way we can reduce it with the addition of these potassium carbonates. We're also looking into other compounds that may work, mainly also metal salts. We're having quite some success with that as well, but unfortunately I cannot talk much about it since there are some patents and stuff that are still pending for that. Yeah, that was more or less what I had. So I guess we can have some questions if you have.